SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process. The challenges provide the chain of opportunity to transform our life. We always be reluctant to face the challenges, but however, if we face challenges bravely using our mind and intellect, definitely we can transform our life in a positive way. Let us now recall what we learned in the last lecture. In the last lecture, we initiated a discussion on cooling system of rocket engine, asking a question, why we need to cool the thrust chamber and the nozzle of a rocket engine. And we learned that the main reason is the non-availability of the material which can withstand high temperature and stresses, or the stresses due to the high pressure and high temperature gases in the combustion chamber and nozzle. That means, if we can produce better material in future, we may not need to have a cooling system. However, at this moment we need to look at it, and the cooling requirements will be more in the throat of the nozzle, as the maximum amount of heat being transferred per unit area at the throat. Therefore, the throat is critical one, and beside this, the combustion chamber wall and other portion of the throat can also be looked at it. And we basically enumerated 5 types of the cooling systems, that is film cooling system, transpiration cooling system, regenerative cooling system, and also the heat sink cooling system. But we initiated discussion on film cooling system, and I have also enumerated how why we call it as a film cooling system, what are the methods by which it can be achieved, and in case of this cooling system, all 3 modes of heat transfer will be taking place. It is not only restricted to the film cooling, it will be occurring in all the other methods as well. We also looked at 4 types of the cooling channels, what can be used, but there might be several others cooling channel design might be available in the literature, and because it depends on the imagination of the designer. Today we will be looking more about the film cooling. Let us now look at a picture of a rocket engine, and which is having a thrust chamber. This is your thrust chamber, and this is this portion, this portion is basically the nozzle. This is having CD nozzle. And keep in mind that these are the coolant channels, and this is without basically any close out. That means, and this is made of copper alloy with machine cooling channels. This machining is not that easy, right? How to machine other things you might have learnt for fabrication or the manufacturing process that you might have studied. And it is quite intricate in nature and time consuming and also costly affairs to that, and the depth of this channel, the size of the channel will be designed by the designer, and also it has to be manufactured properly. And let us look at what are the wall materials and also the coating materials generally being used in case of rocket engines. And of course, as I told, the copper is one which is being used because of fact that it is having a high thermal conductivity. Therefore, the heat transfer will be good, and then it will not allowing the temperature to go up, and rather it will be allowing the heat to transfer to the coolant. And generally the oxygen free copper alloy is being used, and beside these several materials which have been developed, and also it is being proprietary item of the companies, and they have given their name. One of them is Narloy Jet, and the other one SS 347, and SS is your stainless steel, and there are various kinds of stainless steels are there, you might be aware, and 347 is one of them. Gleedcorp, Inconel 718, and Inconel is a very costly material and having higher strength also, and Columbium, and nowadays it is known as niobium, and which is having a very higher hardness as good as titanium, and also it is having a ductility of iron. So, it is considered to be a very good material for wall, and keep in mind that this Narloy Jet is basically copper, silver, zirconium alloy, and this percentage of this copper, silver, zirconium is basically proprietary item, you cannot get to know about it. And Gleedcorp is the trademark product. It is the copper based metal matrix composites alloys mixed primarily with aluminum oxide ceramic particles. Oxide means basically it is a ceramic, and this is again a trademark product. So, Inconel is a family of austenite nickel chromium based super alloys, and if you look at some of the super alloys are used for manufacturing of the thrust chamber and also nozzle. And let us look at the closeout. We will be having S 347 and nickel alloys, copper, monel, and the coating wise, of course, the platinum coating is being used because the catalytic material, and nicro alloy, NICRAIY, and even the soot particle is being coated so that heat transfer will better, and zirconium is being used, and NICRAIY is a basically nickel based thermal spray which is being used to coat the inner surface of the combustion chamber, so that heat transfer can be maximized to the coolant. And various types of coolant can be really thought about, but in case of rocket engine we generally use the fuel if it is a liquid propellant as a coolant, and let us look at some of them which are being used. Basically liquid hydrogen and liquid oxygen can be used, but for that design will be little different, so that it should not corrode the wall of the material itself. RP1, which is nothing but a jet A fuel, and methane and hydrogen peroxide and other also. Of course, you might be aware the water is one of the best coolant what we use in our day to day life, but we cannot use for the rocket engines unless it is mixed with other fuel. Of course, the like jet A can be mixed with water with the help of surfactants, so that you can use as a coolant. And what are the issues in selecting cooling passages? So, to keep the nozzle and the wall temperature below the material limit, that means each material will be having the temperature with which it will be operated, such that corrosion, erosion and also the melting of material will not be taking place due to the heat transfer. That has to be kept in mind, and reasonable pressure drop across the cooling system has to be ensured, so that the whole size, because when you talk about film cooling, then naturally the diameter of the coolant passage also will be playing a role, and if it is a slot, then naturally the size, width of that. So, that will be such that the pressure drop will be minimized, and overcooling is to be avoided, as it is detrimental to the engine performance, because if you take out lot of heat, naturally it is a wastage, and also it will be maybe quenching the flame, and that may lead to problem. So, coolant exit conditions should be suitable for injector and running of a turbo pump, because if it is cooled so much, and then also the turbo pump will be used, because if there is a lot of bubbles which are created due to the vaporization of the coolant, and when the heat more heat being transferred to it, then it will be causing the problems in operating the pump system. So, therefore, that has to be looked at, so that the two phase flow with more bubbles has to be avoided. So, let us look at cooling system of the rocket engines. As I told that the regenerative cooling, that where the liquid fuel generally used as a coolant, and which will be passing through this channel what I had showed you earlier, and this is your channels, and it will be taking the heat from the nozzle. So, also in the combustion chamber, this is your combustion chamber, and where high temperature and pressure gas will be containing, and then this heat which will be taken by this coolant, and again it will be getting into the combustion chamber, such that the whatever the heat transfer to the liquid fuel will be utilized by the rocket engine itself. Therefore, we call it as a regenerative cooling, and it is more efficient than the film cooling, direct film cooling. So, this is generally film cooling. Regenerative cooling is being used nowadays mostly for the large rocket engines and medium sized rocket engines, and it can be used for the film cooling and also the transpiration cooling. Transpiration cooling is basically also known as sweat cooling, because of fact that there will be a porous on the wall itself will be there, such that the coolant will be coming over here and making a very thin layer of film. This will be as if like we sweat, and there is a pores on the skin of us, and whenever the temperature of the body is high, it produces the sweats, and then it will be evaporated and our body gets cool. In similar way here, this is your coolant film which will be created on the both the side, this line if you look at, and then that will be really acting as an insulating layer, and also it will be evaporated, so that the temperature will be lowered down, and that will be taking. Unfortunately, the material for with porous things are not being really being produced, which can withstand high temperature and pressure gases, and that is why it is not being used. However, in recent time transpiration cooling has been used in some cases for cooling the injector head, particularly in case of cryogenic. And this injector head will be somewhere here, because this will be your fuel and oxidizer, this will be fuel, and this is your oxidizer. This injector's head will be here, and it can be used nowadays in some kind of rocket engines, not all the rocket engines, so that the injector head can be protected from the heat generated due to the flame which will be sitting near this injector head in case of a cryogenic engine. So, we will be looking at the ablative cooling. In case of ablative cooling, generally some materials are being used in the throat region of the nozzle such that it can be vaporized whenever the heat will be transferred to here, and it will be keeping the at a lower temperature such that it will be not reaching the critical temperature of melting or erosion of the thing. And in the process, this ablative material will be also eroding with minimally, such that it should not affect the performance of the rocket engine, because if the throat area of the nozzle will be increased, then your naturally it will be affecting the performance of the rocket engine. And of course, graphite alone is not being used, and it is silica phenolic and carbon phenolic material also being used. We will be discussing little more about it, but generally the ablative cooling is being used for a short duration operation such that the heat such that this material won't be subjected to very long duration, and it will be not spoiled the throat area of the nozzle. So, therefore, ablative cooling is being used, but there is another kind of cooling system which is known as heat sink. Heat sink is similar to the ablative cooling, but only thing is that there will not be any ablation or the erosion of material when subjected to the heat. So, generally in the rocket nozzle, if you look at this is your rocket nozzle, there will be some material which will be used, this material which will be used as a heat sink material, like for example, copper alloys is being used, or copper is being preferred because of fact that it is having high thermal conductivity, and this amount of the material which will be put as a heat sink, because it will be taking the heat quickly from here such that the metal will not be eroded of the inner regions. So, this will be dependent on the time, because this time duration for getting the effective heat sink or heat transfer to the heat sink depends on its heat capacity of the material which is used as heat sink, and allowable temperature, and also the heat flux rate. So, therefore, this is being used for a short duration, and particularly for the solid propellant rocket engine, where you do not have liquid fuel to be used as a coolant. And so also the ablative cooling is also used for the solid propellant rocket engines, and we will be discussing a little bit more about the ablative cooling. Let us look at, as I told that earlier, that throat is the most vulnerable part of so far the heat transfer is concerned, because the maximum amount of heat transfer per unit area occurs at the throat region. So, therefore, that has to be taken care, and for that reason what is being used here is the graphite. You might be aware the graphite is having a very high temperature it can withstand, and also it can erode in a very minimal way. So, there are several other ablative materials being used. One is your phenolic resins, epoxies, unsaturated polyesters. If you look at here, it is having a carbon phenolic which is being used. On the back of it, silica phenolic being used, this portion. And in case of downstream of this throat, and this is your throat area, the carbon phenol being used, this is the line what is being used, carbon phenol, and of course, these are the silica phenol being used. Why two materials are being used? That might be a question coming to your mind. If you look at, we will answer that, but graphite and sintered metal are used in the throat, which act as a heat sink. This will be acting like a heat sink. But however, the heat also will be transferring from other places, and this is your again silica phenol backup being used on the bottom of the graphite heat sink. And on heating of the carbon phenolic composite, it gets pyrolyzed and releases the volatile, forming a char. The volatiles will be released, these are volatiles, and it becomes a char kind of things, like when you burn the wood, volatiles gets released, and also a char being formed, which is having a porous in nature. And it ablates around 1400 Kelvin, and not only the carbon phenolic, but also the silica phenolic also ablates around 1400 Kelvin. However, on heating, silica phenolic composite forms a melting layer of silica here, and there is a melting layer which will be formed, and which act as a better insulator because of fact that it has lower thermal conductivity as compared to the carbon. Therefore, the silica phenolic is being used on the back of the carbon phenolic material, and that is why this design is being used nowadays, particularly for solid propellant rocket engines. Let us look at ablative cooling little further. As I told, the insulation and bonding is a must, that has to be bonded properly, and the highest strength of the outer shell has to be ensured. Generally, these are the ablative liners, and the thickness can be varied depending on what you need, and this thickness also get reduced. If you look at this thickness of the ablative liner, right, it gets reduced, this thickness, because as in the nozzle gets expanded, the temperature will be lower. Therefore, there is no need to go for a same thickness of the ablative layer, because one has to reduce the weight of the nozzle. Ablative cooling is quite good for booster and upper stage applications, and firing duration of the rocket engines varies from few seconds to minutes, and as I told, the duration should be small, and it is limited to chamber pressure of 20 bar or less, otherwise this will get deformed, and when assisted by film cooling, it can be used for a chamber pressure of to 70 bars. And pyrolysis resins contained in the chamber wall material keep the temperature of metal below its melting points, and also the operating temperature at which it will not get eroded, such that the integrity of the engine will be at stake. So, with this we will stop over. In the next lecture, we will be discussing about how to analyze the cooling system in case of a rocket engine. Thank you very much.